Imagine a high-performance computer processor. It's capable of millions of calculations a second, right? But it's completely isolated. Without any peripheral inputs, it has absolutely no way to detect temperature, light, or physical motion. And that is the baseline reality for computers, smartphones, and robotics when they're first built. They're just these isolated computational engines totally cut off from the physical environment around them. So today, in this explainer, we're going to look at exactly how we bridge that gap. We're going to see how we give these systems the ability to actually perceive the physical world. Okay, let's dive right in. Seriously, think about it for a second. How does a robot know when to hit the brakes before crashing into a wall? Or how does your phone know when you've lifted it to your ear so it can turn off the screen? How does an automatic door know you're walking up to it? The central processing unit, the brain of the device, can't inherently perceive physical boundaries or human motion. It desperately needs a bridge between our messy, continuous physical reality and its own perfectly organized, discrete digital logic. And that bridge, well, it's a sensor. As our source material outlines, a sensor is simply a device that detects a change in its environment and converts it into a signal that another system can use. It relies on the physics of transduction, basically taking a physical property like light, thermal energy, physical motion or pressure, and magically, or rather scientifically, converting that energy into a readable electrical signal. It translates our analog real world into the electrical language that a machine can actually process. Section 1. The why. Collecting data. So what's the point of all this? The ultimate goal here is data collection. Machines need input data from their environment to execute their logic and make decisions. Without sensors, a machine is literally just a calculator waiting for someone to type on a keyboard. But if we equip them with a highly specialized toolkit of sensors, they suddenly become active participants in their environment. We've got a massive arsenal of sensor classifications outlined in our source text, with each device engineered to detect very specific types of physical phenomena. It's kind of like a superpower roster. Let's look at the lineup. Here's the first wave of that specialized toolkit. We've got temperature sensors that precisely measure thermal energy, giving machines a way to basically map heat distribution. We have light sensors measuring lux and brightness. Then there are pressure sensors for quantifying physical force and mechanical stress. And of course, humidity sensors, which detect the specific moisture content suspended invisibly in the air around us. And the classification just keeps going. Proximity and position sensors give a machine spatial awareness, so it can map exactly where objects are in coordinate space. Sound sensors capture acoustic waves. Chemical sensors are out there detecting specific molecular compositions, like target gases or the acidity of a fluid. And photoelectric sensors use focused light beams to detect when objects break a path. It's an incredibly comprehensive toolkit, so let's dive a bit deeper into a few of these heroes to see how they operate in the real world. Section 2. Hero profiles. The climate controllers. First up, we have our temperature specialists, like the DHT11, the DHT22, and thermistors. Their whole job is to measure ambient heat or cold. Then we have our humidity specialists, like capacitive sensors, which are focused purely on measuring airborne moisture. Now, frequently, these two monitoring capabilities are actually combined into a single hardware module. The DHT11 is a great example of this, allowing a system to log both temperature and atmospheric dampness at the exact same time. To put that into perspective, picture the controlled environment of a classroom greenhouse. By deploying our climate controllers in this space, the system can constantly log the heat and moisture data. If the temperature spikes and exceeds the safe threshold for the plants, the sensor sends out that electrical signal we talked about earlier. The control unit processes the signal, triggers a relay, and boom, it automatically activates a cooling fan. The system is monitoring the environment and regulating the physical space entirely autonomously. Pretty cool, right? Section 3. Hero profile. The light bringer. Moving on, the key hardware to note from our source data here are the LDR, which stands for light-dependent resistor, and photodiodes. These are the components specifically engineered to detect the presence, the absence, or the exact intensity of ambient light in any given space. Let's break down exactly how this works, step by step. Step 1, the LDR just sits there quietly, monitoring the ambient light. As evening approaches, it senses darkness falling. Step 2, that physical change in light actually creates a change in electrical resistance within the component. It then sends an electrical signal to the main system. Step 3, the microcontroller receives the input telling it, hey, it's getting dark out here, and it automatically switches on the straight lights or maybe the smart lights in your living room. It's a totally automated cause and effect relationship based purely on sensory input. Section 4.
Hero Profile, the Motion Master.
When you think of high-tech security, you probably picture that famous vault scene from the first Mission Impossible movie, right? Well, that perfectly captures this specific sensor's domain. The PIR, or passive infrared sensor, is the absolute cornerstone of modern security and motion detection. When you imagine laser grids and invisible alarms, you're really thinking of the practical application of the PIR.
So, how does it work? The PIR detects motion from changes in infrared radiation. You see, everything that gives off heat, and yes, that absolutely includes a human body, emits invisible infrared radiation. The PIR sensor essentially maps out this invisible heat signature in a room. When a warm body moves across its field of vision, the sensor detects that sudden disruption in the infrared background radiation. It triggers an alarm, registering that a person just entered the space. It's literally tracking invisible thermal changes.
Section 5. Hero Profile. Ultrasonic IGCSE 04. Our source material describes this one's mechanism simply but very powerfully. It uses sound waves to measure distance. No cameras, no lasers, just pure acoustics. It acts exactly like a bat flying through a pitch-black cave using echolocation to perfectly map its surroundings.
Here is the 3-step breakdown of echolocation in action for a machine. Step 1. The HCRS04 shoots out an ultrasonic sound wave. This is a frequency so incredibly high that human ears can't even hear it. Step 2. That sound wave travels forward until it smacks into a solid object, like a wall, and then it bounces straight back to the receiver. Step 3. The sensor calculates exactly how long that round trip took, and because it knows the constant speed of sound, it can perfectly calculate the precise distance to that wall. The result? The robot hits the brakes and stops before crashing, all just by processing its own acoustic echoes.
Section 6. The Specialists. Sound, chemical, and pressure.
Before we wrap up, our source material highlights some incredibly practical, everyday use cases for these specialist sensors. We have sound sensors, basically microphone modules, that process acoustic levels, which is what allows you to trigger a relay just by clapping your hands. We've got chemical sensors, like gas detectors or pH probes, monitoring environmental safety by sniffing out invisible dangers like gas leaks or toxic water acidity. Pressure transducers measure the physical force of a fluid. That's the exact hardware your car uses right now to monitor your tire pressure. And photoelectric sensors use focus beams of light to detect when an object breaks a path, which is heavily utilized in manufacturing to count products moving rapidly down a conveyor belt.
So we started this explainer with an isolated processor, completely cut off from the world. But as you've seen, by integrating sensors, measuring light, thermal energy, infrared radiation, sound waves, and pressure, we give these digital systems the ability to quantify and react to the physical world with a precision that often exceeds human capability. Which brings us to a final thought. Take a look around the room you're sitting in right now. What turns on automatically? What regulates the temperature? Where are the embedded sensors monitoring, measuring, and processing your environment at this very second? I really hope this explainer has changed the way you view the hidden technological infrastructure all around you. Until next time, keep exploring.